Okay, hello everyone. Welcome to Join Space Observations and Sustainability course. Today's title is Application of SAR Image, and the lecturer is Professor Chung-Pai, and he's from National Central University Research Center for Space and Remote Sensing, and his research interests are structural geological data processing, and geological remote sensing. Okay, Professor Zhang, please.
Okay. Hello, everyone. My name is Chung-Pai Zhang. Firstly, I will share my PowerPoint with you. Okay, wait a minute. So I think that you can see my screen right now, right?
Yes, very clear.
Okay, perfect. So before jumping into today's lecture, firstly, I would like to show you this image. Let's look at the real case from the southern Taiwan. This is the location is right here in the southwestern Taiwan. This is a village over there. You can see here in the valley, and it's in 2009. A very huge typhoon struck southern Taiwan. It's a typhoon Monaco, shown here. And then this typhoon causes a lot of disaster in Taiwan, including the landslide, inundation, and so on. So in these two images, between these two images, you can see very clear the image before the typhoon, not small. Actually, the habitation is more than 600, I think, a village here, and then during the typhoon event, a large landslide triggered by the rainfall and the landslide material totally cover all this village. It's totally buried by this landslide. So this kind of event, actually, you can easily, or we can say, we can observe that directly by comparing two optical image. And we can use different sensor, different technique, use a different image to compare this kind of disaster. For example, for this, the same one for this village, the Shaolin village, we can see the image acquired by different. Wait a minute. By different sensor, and we can zoom in the area to compare the situation before here and after the typhoon event. We can know which houses disappeared and what damage causes after this typhoon. Okay, but this is for the event that occurred during very short time, and you can see the difference directly between the optical image. But the question is that for the optical image, optical remote sensing, actually we can see the surface change. We can do the detection very quick. But however, for the slight and the largely distributed deformation, for example, the lens subsidence, for example, the creeping along the fault, actually is impossible to be detected directly from the optical image. So we can use another technique that I want to introduce you today. It's a SAR application. So the SAR actually, simply put, it is the satellite radar image. But why we use this term SAR? I will explain you later. Actually, it's an advanced radar satellite. The first one is the CSAT, be launched in 1978, and then we have a radar set, we have the EIS-1, EIS-2, launched by the European Space Agency, and EMISAT, and so on. JIS, launched by Japanese. Cosmos SkyMed is Italian satellite, and the TerraSAR is a Germany high-resolution satellite, and AROS 1 and 2 is Japanese satellites. And some very, we can say the new generations radar satellites, including the Chou and the Sentinel-1 and Sentinel-1A and 1B launched by ESA. That's a very important satellite system because we can obtain this image for free, and we can do a lot of application based on this image. Later, I will show you how to obtain the image, how to for free. And NASA's radar satellite, the NISA, and so on. So for the Sentinel-1 and B, these two para-orbiting SAR satellites launched in 2014 and 2015, I think. But unfortunately, 1A still worked well, but the 1B, I remember it's the end of last year because of solar storm. It functioned not very well. So based on this formation flying, I mean Sentinel 1A and 1B, before we can have a 6-day revisiting interval. But right now, 1B is not, situation is not very stable. So with the revisiting interval decreases to 12 days because we have only one satellite, only 1A functioned. So this is the orbit of these two satellites. So we can see it covers almost all the area of the Earth, and then they have different observation mode, and you can have a very wide swaths, but the resolution is lower, and but the smaller swaths, but the resolution is much higher, and so you can acquire it for free. And here I show you this page to show you how to apply the ESA, the European Space Agency project. And this is contact information. And for the Terra MVSat satellite, you can submit your proposal to this website. And for the Sentinel-1, you can submit to this website. Okay. And normally, if you prepare a good proposal, and after be accepted by the ESA, you can have a quota, for example, 100 or 200 images for free. And with this image, you can do a lot of shows. Later, I will show you what we can do. Okay. And if for today's lecture, actually the time is limited, so I cannot tell you too much the details. If you want to know more details, there are many information that you can find from the website, and I suggest you to read firstly this PDF file. It's a guideline prepared by ESA. Okay, so let's come back to the radar itself. For the radar application, actually this is a history of spaceborne, I mean the radar satellites. It's the first, as I mentioned, the first satellite is launched in 1978. It's a CSAT. But the idea of imaging the Earth by airborne radar actually is it arose in 1950, but after almost 20, 30 years hard working, and then finally they launched the first one, the CSAT-1. But this satellite was soon how to say decommissioned. I mean, phased out. So not many images were taken by used satellite for users. So we can say this is a failed mission. And then different to the previous satellite, the ERS-1 launched by the European Space Agency in 1992. It's a successful launch and remained in orbit for a very long period, very long time, and taking a large number of images for user, and successfully opened a new, we can say, a new epoch of satellite radar remote sensing. And following this satellite, Chou launched. Chou launched in, I remember, 1996, something like that. And you can see actually it's been launched in 1992, and a large earthquake occurred in California. The name of this earthquake is the Landers earthquake. And then is a team leaders. The team leader is Masonet actually, and they use one image acquired before the earthquake, and use another image after the earthquake, and compare the phase of these two images, these two radar images, and to try to calculate the phase difference between these two images. And then they publish the first, we call it as an interferogram of the earthquake. And this paper, of course, is how to say, very important one, and attract a lot of attention and be published in Nature. And for myself, I started to work on this technique and in France, and then we published our first paper in 2001 by using this technique, the radar interferometry, and then to measure the deformation of southern Taiwan. And then, how to say, for this technique, I mean the traditional interferometric technique, there's still some weakness. So we try to develop some new technique to overcome the weakness. And there's right now, of course, there are many new techniques being proposed, including the persistent scattered one. Later, I will show you some results of this one. So today, my topic. Today, I will talk you about the radar SAR application, but the topic in today's lecture include from the radar itself, the traditional radar, to the synthetic aperture radar. The radar, of course, is a radio detection and ranging. Later, we will talk about the principle. And then, in order to see the details of the surface, or we can say the object, so we enhance the resolution by using the synthetic aperture technique. And then we can use this the SAR images to do some calculation, including the interferometric calculation. So we call this technique as INSAR. And then we can use another one, an advanced one. We call it a differential INSAR. So it's a D-INSAR. And some enhanced, or we can say advanced technique, for example, PS INSAR and some small baseline INSAR, blah, blah, blah. I don't want to talk too much about the advanced technique because they are still in developing. So I just stopped here for the PS INSAR. So let's today we have almost 2 hours. So let me introduce you one by one from the radar to SAR to INSAR, D-INSAR, and the PS INSAR. Okay. So what's the radar? The radar is an acronym for radio detection and ranging. Of course, it's a use microwave at the microwave region of the electromagnetic spectrum, and they use the microwave to launch the wave and touch the object and receive the return signal and to detect the object and then measure the distance. So a sensor transmits the original wave toward the object and detect the reflected wave and use the time delay to calculate the distance between the object and the receiver. So the idea is very simple, but you know the earliest radar were designed for military purpose. So for example, the object sometimes a ship or sometimes aircraft and so on. So, but for the pilot For example, if the pilot want to avoid the detection of the radar, so they can, the aircraft generally will fly to the sea or land surface as close to the land sea surface as possible. So as this result, the reflected signal of the aircraft, the aircraft will be mixed with the reflected signal of the sea or land surface, and will be very difficult to be detected. So in this very earlier stage, the retinal signal from the land or sea surface are noise. Only the retinal signal from the object itself, from the aircraft, that is a signal. So we have to remove, or we have to filter the noise from the land or sea surface. So this is the very first idea, very early idea. So for the microwave spectrum, we know it's normally from 1 meter to 1 centimeter. Okay, between this. Okay, and I will show another figure. Okay, this one you can see the wavelength from the Ka band. It's the shortest wavelength radar wave. It's around 1 centimeter to the longest is a P wave. It's almost from 30 meters centimeter to 1 meters, 1 meter. Okay, 100 centimeters. So for the remote sensing purpose, for the satellite remote sensing, normally we use the wavelength not too short, because for the too short, the noise will be too high, and not too long, because if it's too long, the resolution will be too low. So we use from X band normally to L band. For the L band, you can see the CSAT, the first satellite. The payload was C-band, and the JERS and RLOS, both Japanese satellites, are installed with the C-band radar. And for most satellites, actually, we prefer to use the C. Excuse me, I forget. For these two Japanese, they prefer to use the L band. Okay, the penetration capability is higher, but the resolution is lower. But most satellites actually we prefer to use the C-band radar. Its wavelength is around 3 to 6 or 7 centimeters. Okay. Okay, so as I mentioned in the first this slide, that the retinal signal from the land or sea surface firstly is just a noise for the users. But after the Second World War, the scientists think that maybe we can use the retinal signal from the land surface to generate an image. So the idea is very simple. Actually, we just change the looking direction of the radar, and then we can obtain an image. A so-called image actually is not an image, it's just a retinal signal, but we combine this old signal to generate an image. The idea is that side-looking airborne radar. If you launch a radar pulse, and then you can receive all the retinal signal almost at the same time. So all the signal will mix all together. But if you launch the signal toward one direction, for example, like this aircraft, it's launched the signal only to this. It's the left-hand side, okay? Only to this direction, and what will happen? You'll see along the ranging direction, this signal will touch the land surface and return to the aircraft earlier than the far-ranging area. So along the ranging direction, you can have a time delay from the near range to the far range. And then if you receive all these signal from along with time, from the 0 to, for example, to the 18, and then you can see the near range. Firstly, there are no much return signal, and when the signal touch the house, house here and the house here, you have a return from the house very strong pulse. And then for the tree, the return signal is you can see the very clear peak, but it's weaker than the signal from the house. So this is along the range, and then you can scan range by range along the flying track, and then if you combine all these signals together, and you can generate a radar image. So the idea is that side looking. And so keep in mind that the radar image, we cannot take the image perpendicular to the land surface. Always use the side looking technique to acquire the image, okay, to scan the surface. But so you can have different properties of different object. Okay, this is we can use amplitude of different object to distinguish different object. So, for example, if this is a very flat surface, for example, sea surface or water surface or airport, it's a very flat. So just consider as mirror, and then the radar signal touch the surface and will reflect to the other direction. So in the radar image, it will be a black area. For the forest, the signal touch the treetop and has a scatter of the all direction, and you still can receive some signal like this pattern. And for the cornland, for example, rice field, you can have a different area like this, different pattern like this. And very interesting is that for the mountain, of course you have a peak here, and then this slope face to the satellite. This is the other side. So here you will have a shadow, but it be longer shadow area. And for the slope face to the satellite, you have the stronger reflectance, the stronger amplitude, but the slope will be shorter. Okay, and then for the city, because you have many buildings, so these buildings normally is perpendicular to the land surface, so that is perfect corner reflector. So the retinal signal is much stronger than other area. You can see a very clear, very stronger amplitude of this area. So let's come back to the mountain area. You can see the mountain is a symmetric mountain, but in the radar image, you can see the shape of the mountain is a asymmetry. The reason is that, keeping that you know already that the image actually along the range direction, we use the retinal time. So this is a symmetric mountain, and the A return to the sensor, to the satellite, for example, or to the sensor, okay, it's A prime. At B, this signal return to the sensor is B prime, and C here. So you can see even in geometry, it's symmetric, but along the time. So let's continue. So you can see this mountain actually, in terms of geometry, it's how to say, it's systematic, but because of the image acquired along the range, is by using the returning timing. I mean, so the phase toward the satellite, the phase to the satellite, this slope will be shorter normally, because you can see in this cartoon, for this mountain A, B, C is a systematic, but here for the returning time A prime and B prime is much shorter than B prime C prime. It's why that this slope will be shorter. So normally for the radar image, you can directly use for as an optical image. You can distinguish that the building, the mountain, the lake, the water body, and so on. But keeping that in mind that the geometry actually is already distorted. The geometry mostly for the mountainous area, for the area with the topography, it will be distorted. Okay, so and then the resolution actually of this kind of the resolution of this radar image normally is very low. So it's because of the resolution of the radar image depends on the size of the radar panel. I mean the aperture of the radar. So this kind of radar image we call it as a RAR, R-A-R, is a real aperture radar. And the resolution for satellite, for the airplane is still okay, but for the satellite normally it's too low for observing the land surface. So we have to find some technique to improve the radar the image resolution. So this technique we call it a synthetic aperture radar. So we combine. The idea is that we combine many radar images and acquired from different position. For example, along the track direction, you can see the satellite move from here toward there, and then we acquire the image one by one for the same area, and then we by using the Doppler effect, we can find their relative position along the track direction, and then use for the ranging detection is easy. You just use the same time to find that. But for the along track, you need some special technique that is equal Doppler line. We will try to find the equal Doppler line and try to find the right direction. So I don't want to talk too much the details. You just know that we use many image and combine all that together to improve the image resolution. And this technique we call the synthetic aperture radar. For example, we acquired 1,000 images during 1 second, and then we combine all these images together, and we can enhance the resolution to 1,000 times. Okay. And the resolution for image, for example, a pixel is 10 kilometer, and will reduce, or we can say improve to 10 meters. That is precise enough for remote sensing purpose. Okay, so SAR is a synthetic aperture radar. So let's see an image, a result. This is a real aperture radar image, and right-hand side is a synthetic aperture image from the southern Ukraine. That is a hot area now. So you can see the water body, the land surface is very clear in this right-hand side image, but for the left-hand side is a real aperture. You can see nothing at all, actually. And for example, the Taiwan area is an image acquired almost 20 years ago by the MVSat satellite. And it's a northern Taiwan. You can see our capital city, the largest city of Taiwan in the basin. So you can see very white color. It means that there are many buildings there. So as I mentioned, the buildings are normally perfect corner reflector, so the return signal of this area is quite strong. And for the water body, you can see the a river here and river here, and a dam here, and that is very flat surface. So that's black because it's just like a mirror, and the signal will reflect to the other direction. And here you can see two black lines. These black lines are the airport, the Taoyuan International Airport of Taiwan, and some city and the rural area. And pay attention to the mountainous area. That's interesting. You can see this mountain. Of course, there we have a longer slope and a shorter slope. Always longer slope and the shorter slope, longer here and the shorter to the east. So it means that, and the shorter slope, you can see the returnal signal is stronger than the longer slope. So it means that the satellites acquired this image from the east of Taiwan and look to the west, to its west, and receive the returnal signal from the west to the east. And almost all the satellites, how to say, the radar satellites, the default direction of the looking direction is to its right hand side. So this satellite right now moving, we can know at this day the satellite was moving from the north to the south, and was looking to its right hand side from east to the west and acquire this image. So this is descending mode. And normally the descending mode is in the morning and the ascending is in the night. Okay, so we can say that it's the morning of this day, the satellite passed to the east, from the north to the south, and from the east of Taiwan, and acquired these images. So this is SAR image. You can how to say, to do some classification or change detection directly based on the radar image. Of course, this is no color because you have only the amplitude. Okay, you cannot see any color from the radar images. You have only the stronger or weaker returnal signal, and then you can obtain the geometry. That's all. But still, you can do many things. I will show you some images of satellite. It's EIS-1 satellite. It's launched in 1996. So I took this picture in France, in the southern France, in Toulouse. It's a park. We call it the Cité d'Espace. It's a park of space industry. Okay. And then there's a MVSat launched in 2002. But both these satellites right now are phased out. And right now we have, as I showed you in the beginning, that right now we use ALOS, we use TerraSAR, and also we have Sentinel satellite and so on. Okay. So let's use the SAR images acquired by the, this one is acquired by the, I think it's EIS-2, okay. And to see something, to find something. This is in 2001 to this July and August. You can see here you have a black area and it disappeared 1 month after. It's between these two images there is a typhoon event, and then here we have a barrier lack. It's caused by a landslide and cut the river here, and to generate a natural dam, and the water accumulated after the water natural dam, and to form a barrier lake. And during the typhoon event, because the precipitation was very, very large, and the flood destroyed the natural dam, and the barrier lake disappeared in one night. Okay, so by this way you can see it's very sensitive. The radar image actually is very sensitive for the water body, so we can use that to do many things to detect the water. For example, it's a dam in northern Taiwan. It's a Shimen Dam, Shimen Reservoir. And during different periods, you can see we have a different water line. I mean, the line, the boundary between the water and the land. So you can calculate the water level actually of this area of this lake. And of course, this is very sensitive for the flood event to detect the inundation, even especially during the very bad weather condition, because the radar wave is much longer, than the visible light. So the penetration capability of the radar wave or radar spectrum is much better than the visible light. It can penetrate the cloud and touch the land surface and return to the satellite. So even during the typhoon event, you can see the land surface, the situation of the land surface. So this is southern Taiwan. Is Taiwan, southwestern Taiwan is a Pingtung area. You can see it's shown by the red rectangular. And the blue area here are the flooded area during the typhoon event. And keeping that in mind, during this period, when we acquire this image, this area is covered by the typhoon. Okay, so from the optical satellite, you can see nothing. You can compare these two, this before typhoon and during typhoon event is a 1 week different. And then for the cropland, this area, I think most of this area, for example, this is rural or small town here, and all this area covered by the cropland. And then during the typhoon, you can see all change the color to the black, means that it's covered by the water body. Okay. And for the northern Taiwan, we have also some cases during the typhoon event. And this technique, you can see that it's very powerful for some urgent event, not only typhoon, and also, tsunami event. That is a tsunami event in 2011 in northeastern Japan. That is quite famous one. That's a large tsunami triggered by the large earthquake, and this tsunami serious damage this area, the Sendai area. And you can see the image here. The blue color are the area that we determined by using the radar satellite. This is a TerraSAR. It's a Germany radar satellite. Okay, we enlarge this area, and you can see the blue area, and this area are all the tsunami inundation area, and the airport area you can see. And because this is, we can receive the images of almost the whole area of Eastern Asia from our center, so we can receive the image from the northern boundary of the China. I mean the boundary between the China and Russia to the south. We can receive the partial Indonesia, and to the east we can receive the image of the Guam Island, and to the west the partial of the Tibetan Plateau. So even for the Myanmar area, we can observe that this is a river. This is the Irrawaddy River, and 7 years before there was an inundation event, and here we use the radar image to distinguish that. And not only for water, and also for the oil. I mean the oil underwater surface still we can. Because of that. Okay, it's in order to save cleaning cost. I mean, many oil tankers, but many oil tankers take advantage of bad weather condition and to secretly dump waste oil in the public sea. So because the reflecting signal, that I mean the the surface texture different to the sea surface. So we can use the radar image to detect that. For example, you can see here in the Bohai area of China, and this black area dark is much clearer. That is continuous and solid than the surrounding area. This is sea surface with wave, but this is oil spill. So we can enlarge that to see the details. And also for Taiwan area, we can see also during the typhoon event, it's a Toraji typhoon. It's in 2002. All this area, you can see the wave, the wind field toward the north. So here, during this period, at that time, the Taiwan island was totally covered by this typhoon, and the oil tankers, oil tanker dumped the waste oil in this area and be observed by the radar images. And you can see some details. Okay, some details here also. Okay, this is another event around the small Ryukyu area. Okay, so and also the SAR image can be used directly for the military purpose, and this is in Gulf Aden in Eastern Africa. You know there are some. This is a dangerous sea area for the trading fleet. So sometimes we also use we send some frigate to protect this kind of this trading fleet. You can see the details. This is Martian ship and this is frigate. Okay, I will show you some more clear result in the very sensitive area that is in the Crimea, in the Ukraine. Southern Ukraine, there's a lake here. You can see two ships here. We enlarge that. This is a high resolution image. The resolution is around 30, sometimes smaller than 30 centimeters. So we can see the detailed pattern. Okay, we enlarge these two ships, so we can see the very detailed, because this is side looking, so the radar signal can touch the sea surface and reflect to the one side of this ship and come back to the satellite, and then you can see the outline of this ship and compare that some figure. We know that it's a Kara class, and this one is a Alligator class ship. So, and then also for the area covered by the snow, for example, the Russia area, you can use radar image to see the different retinal pattern. For example, this area is the blue. This is blue color, light blue color. It's a snow that be, how to say, compact, be to by the vehicle. So this the surface is smoother than the other area. So we know that there are some car pass often this area, and we can see some details. For example, this is vehicle tracks. No, here, and this is a building, and you can see some fence around the area and so on. Okay. So that is a technique. Oh no, actually we cannot call it as a technique. This is a method. We can use the radar image and to detect some or to extract some information directly. Okay, we don't need to do some complicated calculation, and we can use that to already you can do a lot of things. But actually, the radar image including combined not only the this direct information. Actually, we have many other information you can use. For example, the phase information, because the wavelength of the radar signal is larger enough to be calculated. So we can calculate the phase difference between the two images and to extract to to find some important information. For example, topography. For example, land surface deformation. And let's have a break for 5 minutes, and then I will come back and I will introduce how to use the phase information in the radar images and to do some advanced study. Okay, so 5 minutes. Let's come back. Let me see. 2 minutes before 5 p.m. Okay, local time Taiwan.
Mungze, are you there?
Yes.
And you can show the certificate to the people, during this time. So, this is Wang Yip. Yeah, I'm one of the organizers of this course. And one thing we have been thinking, but not yet talking about it, is that we are thinking that at the end of this course, that means maybe 3 weeks away, we would have one more session. But that session is to invite you who are interested. If you say you have learned something, or you want to discuss your problem, your research problem, your question. And I will also invite the professors, the lecturers of this course to come to here, so that that they might, if they're interested, then they could work with you. So that is one of the possibilities, and we would describe it and announce it once we have consolidated the idea. So just I hope that if you're interested, please write down and say that indeed I have something that like in this talk that you think, oh, this is something that I want to do, interested, and because I have a problem which can be using can use such a method, and then you could start thinking about a small project, an idea, and hopefully it could interest Professor Chang, to work with you, right? So that is just one possibility, and you could even think about that with other professors, other lecturers in the previous session, right? Okay, I hope that you will be interested in such a possibility. Okay.
Okay.
Welcome back.
I'm back. So let's continue our lecture. Okay. So already the very basic use for the SAR image. So I will talk to you about some advanced calculation. The first one is the interferometric technique. So the idea is that we can combine two radar images.
You have to off screen.
Professor Chang,
it's me.
Professor Chang, you have to reshare your screen. Yeah.
Okay. So the idea is that we can use two images of the same area, but acquired of a little different position. I mean, the baseline difference is very, very slight. For example, 100 or 200 meters, sometimes smaller than that. And by compare these two images of the same area, and using the baseline difference, you can calculate the phase difference of the images. And then this image sometimes can reveal, or we can say can show you the elevation of the target area. So the idea is in SAR, okay, interferometric SAR. So the perpendicular component of the baseline is important for estimating the changes of an intervariable pair of SAR images. I don't want to show too much the details. I just use this cartoon to show you the most important principle of the INSAR. So this is mountain, small mountain here. You have the elevation is h. Okay. So you acquire the image of the mountain from this position, and then maybe 1 month later or several days later, you acquire another one here. We call it the master track and the slave track. And you can compare the baseline here. The parallel baseline is not important. We just use a perpendicular baseline because parallel baseline, the effect will no effector for without containing any effector of the elevation. Only the perpendicular baseline can be calculated. It's useful. So, and then after blah 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 blah, we just obtain this formula. It's a HA equal to the one number over the perpendicular, this one, perpendicular baseline. And HA, we call it the attitude of ambiguity. Okay, HA. So what means the HA? It means the effect of the orbit. Okay. Let's check again. This is the only one formula in my today's lecture. Okay, so just be patient a little. If the baseline is 94 meters, for example, 94 meters, a little less than 100 meters, and then you will have a HA of 100, and this 100 means that every 100th of elevation, you will obtain one fringe, just like this one. This is a peak of the mountain. This is a volcano, the mountain Etna. And if this value is 94, and then the interval between the contour, the contour interval will be 100 meters. Means that you can use this interferogram as the contour map. And this is elevation, 100, 200, 300, blah, 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 till the top of the mountain. So you can extract the topography of the mountain and the elevation of the mountain. Okay, so of course I skill many details. You just keep that in mind that baseline, perpendicular baseline is play a key role, the most important role to generate interferogram. And if this is larger, and then this will be smaller. And if this is baseline smaller, and this will be larger. If this is zero, excuse me, you cannot extract any topography information. But if this is larger, it will be very useful, very sensitive, okay, to track to extract or to calculate the topography. But if it's too large, it's too complicated. Okay. So based on this technique, the space shuttle actually they installed two radar, two SAR in the space shuttle, and then scan the land surface at the same time. You don't need to wait. You just scan that at the same time, and the baseline perpendicular here, perpendicular baseline is fixed, and quite at the same time, so you can calculate, you can extract the topography very, very fast. So we call it the SRTM, Shuttle Radar Topography Mission. And they use two different arrow band wavelengths longer, C-band wavelengths shorter, so we can see this is more precise than this one. So you can obtain, download the SRTM, global SRTM for free right now from the USGS website. And just like this one, it's a Turkey area. And then that is the INSAR technique is only for generating the topography. But let's come back to this one. If the baseline perpendicular is zero, what will happen? You will have no elevation effect. You can see nothing. You cannot generate the elevation model. But if you still see some fringe, if you do the calculation, the geometric interferometric calculation, and you still see some fringes, what's meaning? what means this fringe? It's maybe it's a deformation. Of course, you have to remove the orbit effect. You have to remove the topographic effect and the atmospheric effect and so on. All removed, and then the information is made. We can say that is a deformation result. So the first difference between two images taken from the same viewpoint, I mean exactly the same point, but at a different time, and can precisely measure any shift of the retinal phase. So removing the topographic orbit and blah 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 and so on, and may reveal the ground movement along the line of sight between the radar and the target. Keep that in mind. It's along the line of sight because only in this direction. But you don't know it's a horizontal movement or vertical. But sometimes with some GPS or other GNSS or some other level data, you can calculate that. But for the calculated result, I mean the interferometry result, we see directly the line of sight deformation. I mean the deformation along this direction. Okay, so let me use this cartoon to explain you this technique again. This is also from the mountain Etna. Okay, so it's in 1993 after an eruption, and the volcano is like this one, the red one. Okay, it's a little higher, and the satellite passed this area and took one first radar image. So you can see the red wave shows the radar wave touch the surface and return, touch the surface and return. And 1 year later, the volcano cooled down a little. So it's of course there are some subsidence occurred in this area after the erosion 2 years later. And then satellite passed through the same area and took the second image. I show the topography of this volcano is the blue line and the blue track, and the blue wave shows the wave radar wave of the second track. You can see for the far field area, because there's no subsidence, so there's no phase change. Toward the volcano center, the subsidence is larger and larger, and the distance for the radar travel will be longer. So we can see the blue wave will go a little longer and come back to satellite. So there's a half wavelength for this area. And if the subsidence is a half wavelength, and then because it's a go and a return signal, the satellite received the return signal. So the phase change already one wavelength. Only half wavelength of subsidence can generate one phase change. I mean 2π of phase change. And we can use the rainbow color from blue to red for these 2πs of phase change. So we can see from here, half wavelength of subsidence, one wavelength of subsidence, 1.5 wavelengths of subsidence. So you can have a 2π, 4π, and another 2π subsidence. And this is a real case. So here, each circle of fringe corresponds to 2.8 centimeters of subsidence. So we can calculate the subsidence field of the volcano. From here, far field area is 0. And toward the volcano center, 6.8 centimeter, 5.6 centimeter, and 8.4 centimeter of subsidence in the volcano center. So we never been there. We didn't carry out the field work or field measurement over there. We just use 2 images, one just after and one year later. Right? Using these 2 images, and we can know during this 1 year there was a subsidence of 8.4 centimeter of this volcano, central volcano. So it's a very economic and rapid and efficient, very useful technique for the land surface observation. So compared with GPS, you don't need to go there to do the real measurement. So as I mentioned in the beginning, that in the 1992, the EIS-1 has been launched, and then the Landers earthquake occurred along the St. Andrews Fault. So the MasoNet and so on, they use the image acquired before and after the earthquake, so to generate this pattern, this interferogram. The black lines here show the fault line. Okay, so this is a Tri-C fault. This is left lateral fault. It means this party go to the go up, and here go down, and you can see the pattern of the deformation associated with the earthquake. As I mentioned, the one circle corresponds to 2.8 centimeters, so we can see the deformation field is quite large. The deformation amount is quite large. So, of course, this is a very important result, and then published in the Nature, and has been chosen as the cover page of this issue. Some French here, so if you want, you can read the French. The image d'un tremblement de terre. Tremblement de terre means the earthquake. Okay. So, and also this technique has been applied for the Taiwan area since just after that, and we published our first paper of the Tainan area. Tainan is a big town in southern Taiwan and located on a tableland. And since many years ago, the geologists think that this area is still active. Maybe not caused by the fault, by actual fault, but by the mud that appear under the city. So it means that there's mud uplift the soft mud with water, something like that, and uplift and hold this tableland and uplift the city at the same time. And we use several images to calculate. This is a topographic map. Tainan tableland, the city is just located on this tableland, and we can see the uplift pattern very clear. And of course, this technique not can be used for volcano, but for the uplift of volcano deformation, for the land surface deformation, and also can be used for the glacier area. For example, we can see this some result from this is not the result from our land, but from our colleague. They find some new crack in the ice sheet and here, and to calculate the movement of the glacier. Okay, and then I will show you some real case in Taiwan. This is how to say, it's not a very new case, but still that is that is very easy to understand how to apply this technique. So I use these some old cases. So from the south to the northern Taiwan, from Pingtung, central Taiwan, you can see a river area as a river. This is the largest river in Taiwan, and the second one here. So we see some deformation. Principally, they are then subsidence caused by the water pumping of the flooded plant, and also for this plant, and some water pumping here, and false cases from Taipei City. And okay, let's check one by one. The first one is from Pingdong. You can see the fish pond. That it was very common in this area. And for this fish pond, they pump a considerable amount of groundwater from this area, and especially during the winter, because in winter this area is a dry season. Another reason is that in the winter the temperature is too low, and for saving their fish or make a more comfortable environment for their temperature for their fish, the agriculture they pump the water, the groundwater is normally the temperature higher, is warm water, so for their fish pond. Okay, so let's check the result. So first, very early result is I did that in when I was a student in France. We found that there is a serious, very quick subsidence in this area. These images all acquired in 1996 from we use one image of the January, and the other one is from February, March, April to May. So the time interval of this one is just several days, 1 month, 2 months, 3 months, and 4 months. Okay, so for this one, of course, you can see nothing. There's no subsidence, and then we see some pattern here, and the clear fringe here, and the finally during just only 4 months during this spring, no winter to spring, we can see 2 fringe. As I mentioned before, that each circle fringe corresponds to 2.8 centimeters. So during only 4 months, a subsidence of more than 5 centimeters occurred here. That's quite huge, quite fast. So it's why that the length of during that period from 1990s to 2000s, each typhoon can carry the huge damage for this area. This you can see after the typhoon, and all cars here are covered by the mud here. So this flooded area. And after this observation, this study, we know that the local government try to stop this rapid subsidence. So they start to check the wells, try to check the fish ponds, and how to say, stop this water pumping. And then you can see the result is that the subsidence ceased, stopped slower and slower. But still, we can use several years data to check if this is real, the water pumping caused this subsidence, or it's caused by other fact. So you can see this figure from this is the time. The cross axis shows the time from 1996 to 1999, and this is daily rainfall. And you can see from the April to August to the October, this is the rain season and the dry season, and the rain season and dry season and rain season. So during the winter, the rainfall is very, very less, even less than 10% of the annual amount. So we use the image pair of the dry season, wet season, dry season, and wet season to compare the different. So for the dry season, D1, D2, and D3, and wet season, W1, W2, and W3, you see the results. For dry season, the subsidence pattern is very clear. You can see fringe 2, fringe 1, and 2, and so on. For the wet season, there's no pattern, no fringes, means that maybe there's no subsidence. And then we compare with groundwater level. This is wearing data from this cross axis shows the times from 1995 to 2000. And you know the time period of dry season, D1, D2, D3. There, here, D1, D2, and D3, you see clear subsidence, and then the red color shows the groundwater table from the drilling data from the 1, 2, 3, 4. This 4 is from here, and the 5, 6, 7 from far field. And for this 1, 2, 3, 4, you can see very clear pattern. There dry season, there subsidence, wet season, uplift of the groundwater, and dry season, wet season, dry season, wet season. And so we can conclude that during the dry season, the local people pump the groundwater to cause the land subsidence. But during the wet season, the groundwater come back. The groundwater level is higher, but the land surface cannot be uplifted by the groundwater. It is still stay at the same elevation, the same situation. But for the next dry season, when we pumped again the groundwater and land subsidence occurred, and then the groundwater come back, but the land surface still keep the same situation. So the subsidence is not continuous, it's a step by step. When you pump the groundwater, it's subsidence occurred, but when you refill the groundwater, it's very difficult to be uplifted. I mean, the land surface is almost impossible to be uplifted, or we say the uplifted amount is too less to be determined. Okay, so for the Taichung area, Changhua area is the same situation. It's a large river, so all this area, this plain, 90% is covered by the rice field. So you can see, I show you directly the result. This is our D-SAR result. You can see the subsidence pattern like this. And this result is a labeling. We measured 1 point by 1 point from this point, and this is interpolated result. You can compare this interpolated result with our SAR result. You can see it's quite similar. And if you compare along these two tracks, this is a major point, and then 2 lines of measurement, A, B, and C, D. You can see actually the results very, very similar. So it means that it shows that our this technique is very powerful, and the result is good enough for many study. Okay, and for the Taoyuan area, it's the same. It's a many similar case, but it's an interesting one because you can see here you have one subsidence center here, or we can see a fringe pattern here, a circle in shape. We enlarge this area, you can see from here to here is a here, no pattern, and the start here, and continue, and continue, and stopped again. So it's the time series is from 1993 to 2003, during 10 years. And this pattern, if we put that along with time, this is it's a cross section of this area, and this is time from 1993 to 2003. We calculate the subsidence amount of the center. I mean the center here, the center here. You can see the subsidence occurred from 1993 and reaches the largest amount and come back a little. And if you calculate the subsidence rate, I mean the subsidence rate of the center, it's firstly not very fast, and larger and larger, and then stop and a little uplift. So we went there to the center of this area. We found that it's a industry park, and in the industry park there is a factory, a large factory of steel. Metal, I mean steel factory. So they pump the groundwater for its cooling season, and then this factory moved to the mainland China in 2000. So you can see the pattern is very dramatic. Subsidence occurred, accumulated, and faster, and stopped very briefly, very clearly stopped here and come back to the a little lightly uplift. It's just they just stopped the water pumping, and then the subsidence stopped very at almost the same time. So it's an industry case. It's not for the aquaculture, not for the agriculture. And for the Taipei city, we try to apply this technique for the Taipei city, but the result is very bad. I will show you the results. We can see only some pattern in the basin, but for the surrounding area, we can see nothing. As I mentioned in the beginning, that for the mountain area, for the city, for the metropolitan area, because there are many buildings, that is a perfect corner factor, so we can have a very good interferometric result. But for the surrounding area of Taipei, we come back to this one. You can see that is a mountainous area, and for the mountainous area, the topography is one problem. The topography is too complicated, so you have to remove the topographic effect, and even you remove that, the vegetation is another problem. You can see the green color here shows that this area is covered by the tree. So the vegetation is another problem because the coherence between the two images will be very low, and without the coherence, you can not find a good pixel to calculate the phase of this pixel and to do the interferometric result calculate. So for the mountainous area, it's a weakness. Is a we can say weakness, or we can say a limit for this SAR or SAR technique. So we have to find some other advanced technique to overcome this problem, this limit. Later, I will show you another one advanced technique, but here I will show you another application case of the SAR. This is an earthquake event. In 1999, a large earthquake occurred in central Taiwan. It's a Chih-Kuei earthquake. It's the magnitude reaches 7 point. I think I'm back. So this earthquake occurred along the Chulumpu Fault. This is the outcrop of the Chulumpu Fault. You can see the uplift of the hanging wall side is almost 2 meters, almost 2 meters. This guy was my classmate. He was around 1 meter 80 centimeters. So you can see the displacement amount is quite large. So after the earthquake, of course, we can arrive there to measure the in situ movement along the fault. But for the deformation of the hanging wall side and the foot wall side is still almost impossible, because before the earthquake, we didn't measure the point by point of all these areas. So here, right now, after the earthquake, if even you measure all these areas, very details, you cannot compare with the topography of pre-earthquake. But we can use the SAR technique to do that. Firstly, we can download some images acquired before the earthquake, and then we acquired some image after the earthquake, and compare them directly and to calculate the phase difference. I'll show you the result. Here, this is time. The cross axis shows the time, okay, of the 1999. The earthquake occurred here in September. So we use one image pair here is A. The result is A. Two images including the earthquake, B and C, and the D after the earthquake, without the earthquake event. Okay, so you can see A and D. You cannot see the clear pattern, but for these two interferograms, with including the earthquake event, you can see a very similar pattern. This is the Trompu fault, the earthquake fault, and then you can see in the hanging wall side, you can see a very beautiful fringes. This is co-seismic fringes, and we can calculate a lot. Each fringe corresponds to 2.8 centimeters. So you can unwrap this result into this figure. This figure just shows you the displacement field by meters. You can see here the red color shows the largest deformation occurred during the earthquake. It's almost 30 centimeters. And this calculation is based on this technique. We call it as a phase unwrapping. It's a one fringe, two fringe, third fringe, and then we take it all together and to generate this one to generate this one. Okay, and we can compare with the GPS data. It's quite consistent, and then we can see the deformation pattern of the lower part at the footwall side. Again, we have to come back to this one. Here, you can see the beautiful fringe here in the footwall side, because here is a plain area, it's the metropolitan area, so the coherence quite good, and you can have a good interferometric result. But for the eastern side, this is mountainous area. The hanging wall side is a mountainous area covered by the dense vegetation. So the result is very, very bad. And the other limitation is that the displacement during this event, during this earthquake event, is quite large. It's almost 2 meters. So if you can extract the fringes of this area, you will have very, very dense fringes, almost more than 100 fringes here. So it's very, very difficult to be unwrapped. So this is the limit of the inside. And so you can see in this result, I just put the result of the western side of the in the western side of the Trompu fault. For the mountainous area, still we can put nothing. So we have to develop some new technique. Not only the vegetation, but also the topography, the orbit, the weather, the atmospheric effect, and so on. So we have to remove all these one, and then we can obtain the interferogram. But for some area, it's very, very difficult to be removed. For example, you can see this case. This is interferometric result, and this is optical image. For the green area, means that covered by the vegetation, you can see nothing. Only in the barren area, you can see the rock directly, and you can have some result. And for the atmospheric is the same. It's an interferometric result of 2 images acquired of the same area, but the time interval is only 1 day. But it's a very very different weather conditions. So you can still see the atmospheric and ionospheric result still in the interferometric result. Interferogram. Even there was no deformation during these 2 days. Okay. And the other is time. No, this is one is a perpendicular baseline. It's a baseline is too long, and the coherence will be too low, and then you cannot generate a good result. And the other one is time. For 4 months, the coherence is still good, but for the image, the time interval is 8 years. You can see the result is very bad. So, in order to overcome all this, we developed a technique with our colleague in England. It's a persistent scheduled INSAR. So we don't use all the pixel. We just choose some stable pixel. I just show you the very simple idea. Okay, the principle of this one. So we just use the scatter that is very stable in all these images. And we use not only 2 images, we use a series image as small as possible, normally more than 20 images together, and choose the stable pixel of in all these images, and then we calculate the phase change of the single pixel along with time. We don't calculate it with for the how to say for all images together. We just calculate the pixel by pixel, and then to show the change along with time. I mean the change of this pixel along with time, and to find the deformation one by one pixel by pixel. Here I prepared some cases, but I think we don't have time to see all these. I just show you maybe one or two. This one is from the same area, the Geospatial River. This area, you know that for the inside result, you can see very beautiful. I already show this result in the inside result, but the PS inside, we can see this almost the same pattern. The red color shows the main subsidence, the subsidence center, and this dashed line shows the high-speed rail in Taiwan, and it passed through exactly the subsidence center of this area. You can see subsidence rate quite fast, 6 centimeter per year. And then you can still see some, because this is we calculated that pixel by pixel, so we can see the results mainly from the road, from the building, and also from the bridge here over the river. You can see the bridge. You can see the very detailed pattern. Actually, this technique we applied in so many different areas. For example, Hanoi, and we can calculate the deformation of the Hanoi downtown, and also we see the deformation of even one bridge. Okay. So you can compare this result with, of course, level data is quite similar. This subsidence center here and here, and of course, this is you can see each pixel here can represents one major result. So the density of this measurement is quite high, and we know the subsidence occurred in this area since long time. So many different kind of measurement has been applied for this area for more than, I think, 30 years. So, but right now we have more detailed results, and we can compare with different measurement, and we find something interesting of this area. I will show you. And this is very recent result till almost right now, from 1993. The DINSA result from 1993 to right now. So almost 30 years. And then we compare this result with a local measurement, including the whale data, and we compare the shortening, the shortening in the whale. You know, if you pump the groundwater from a whale, and then the aquifer will be compressed, and then the whale will be shorter. And we have a measurement from the land surface, and we want to know it's occurred in which aquifer of under this area. And the result is quite strange and quite surprised, is that you can compare directly this one. This is a whale from one location, and this, no, excuse me. This is whale data from one location, and this is our major result, and it's quite different. And we come back to that here. And our result shows that the surface deformation here, you can see, for example, here accumulated the result is 4 centimeter. No, this subsidence rate is 4 centimeter here, and then we calculated the whaling data, and we find that underground for the deepest well is around 400 meters. So during this 400 meters, we can observe only around 2 centimeters of shortening. But the subsidence of here is 4 centimeters. It's just an example, 4 centimeters. But the shortening in the wells is only 2 centimeters. It means that if even we don't pump the groundwater, because of the wells are short, normally it's not so deep, it's less than 400 meters. So even we stop all these wells, we stop the pumping water, we don't we don't use the groundwater for the agriculture of this area. Still, there are 2 centimeters, half, 50% of subsidence. We don't know from where, maybe from the lower part. So right now we have to measure the lower part. We want to use some geophysics method to measure to observe the structure of the lower part and to know what happened in the lower part. So that is an interesting topic. And then I skip, because time is limited, I skip this topic, this area, the Yilan area. I will come back to the Taipei area directly. For the Tien-Yin SAR study, I show you the result of Taipei Basin is quite bad because the active fault, or we can say active deformation, occurred normally between the mountain and the plain, or the mountain and or we can say mountain and the metropolitan area. So this is maybe a fault. We call it the Sanjiao fault. There is another fault, and there may be another fault. We don't know. But since we can observe only deformation between or in the basin, so we cannot compare, we cannot reveal the real deformation between mountain and the basin. So we try to use this technique, PS-Yin SAR. Sorry, maybe I forget to mention that. This persistent scatterer Yin SAR technique try to find the deformation of the Taipei and the surrounding area. Physically, this PS scatterer, this persistent scatterer can be the big rock or electric tower or isolate house in the mountain. So we just use this pixel to calculate the deformation. And let's see the result. This is our result. You can see still from the mountainous area, we can see many points. And here, between the basin and the Lincoln tableland is not very clear. I mean, you can see the color is continuing. But for the northern part, here we think that there may be some structure here, but proposed by geologists, but we never observed the activity, or we never measured the displacement rate of this area. And from our PS-Yin SAR result, you can see we compare along the X to X prime. We compare the result from here, and we can compare with this B line, and what we can see. All these dots, these points are our result. I guess prime. Excuse me. Okay, it's this one. Now let's come back to this one. Let's check firstly from the line B. This is a leveling result. The triangular point are the major leveling results. We compare this leveling result with our PS-Yin SAR result directly. These pixels are our PS-Yin SAR result, and you can see is this one. The small points are our PS result, and this line is the leveling data, and this is A1, A line, line A. Still, you can see this is small point our PS result, and this is leveling data. You can see some displacement occurred along this fault. And if you check this X prime from here to here, you can see this part and this part is relative uplift, and this part is relative subsidence. So maybe here and here between these two blocks, there are some displacement occurred during this period. So let's come back to see the topography of the Taipei Basin. We look toward the north, from the north to the south, excuse me. So it's a volcano, and this is a Lincoln tableland, this is a tableland, and this is the basin. It's a triangular in shape. If we remove, right now it's covered by the buildings, and it's the most important economic center. Actually, it's a capital city of Taiwan. But here you check the actual fault of Taiwan. Here, the western boundary of the basin, some black line shows the important fault. Very difficult to be measured because it's ceased. It's not very active, but we believe that it was active. This line, okay. Because in 1694, actually, this is from a historical record. It's a Monsieur Yuan heard of Qing dynasty. He arrived in Taiwan in 1697. Okay, when he arrived here, he found that the Taipei Basin was covered by the big lake. Okay, right now it's a basin, but it was a big lake that moment. And Mr. Yu asked some local people, and people told him that it's before 3 years before. It means 1694, because he arrived in 1697, so it's 1694. There was a large earthquake occurred in this area, but they don't know, of course, which fault generated this earthquake. And then the water come from the from the sea, and come fill all this area and generate Taipei Lake, or we can say Old Taipei Lake. So we think the fault should be one of the surrounding fault. And then if you compare this geological result, this one is the most possible candidate. And this is the lake, the map in 1770. Still, you can see this is the outlet of the Danzi River here, some shipped here. So you know this Taipei Basin is covered by a lake, and 30 years later, the lake has disappeared. So we know that maybe this is a circle. Once the earthquake occurred, and then subsidence along this fault, and then the Taipei Lake generated. And then several years later, this lake filled by the sediments, and then the people come back to the basin. So this is a model. We just show you if the displacement is 1 meter, 3 meters to 7 meters, is how large the Taipei Lake is or will be. And we think 3 meters is large enough to generate such a big lake. And this is a SAR image. We just simulate the lake that described by the Mr. Yu in his book. And right now, of course, we have a very complex. We have a lot of geological data from this area, and you can see the basement of the Taipei Basin. Here to the western side is deeper, and the eastern side is shorter. Is shallower. So just like this one from east to the south, this is a field. This is the sediments. The shape of the sediments of the Taipei Basin. Okay, and under the sediment is a basement. Means that this is a real mountain, but right now it's under the Taipei Basin. And if we remove all the sediment, you can see the shape of Taipei Basin is just like this. This is the basement of Taipei Basin. So-called basement was the mountain before. So along this line, we look to the south, to the south. So this line actually is this line, and this is the shape of the basin. So you can see here steeper is a shallower. So before all this is a mountain, but because of the displacement along this fault, so this part subsidence along with time and right now generate a triangular shaped basin. I mean the basement of the basin, and right now the basin after many times of inundation, and then to generate a very flat area, a flat basin, and right now it's a Taipei Basin. So it's a model of this area, and we can compare this model with our observation. Right now, the displacement along this fault is not so active, but still we can see in the northern part, it's still a little, how to say, the creeping. You can still observe the small creeping, and some uplift in the other area is maybe caused by other tectonic mechanism. We don't have time to discuss that too much. But in this result, we cannot observe the very clear the displacement along this fault line, but it's a good thing. This means that right now it's stable. But just like a Chulompu fault, the case from the Taichung, I show you the Chi-Kuei earthquake. After the earthquake, you can observe, we can calculate that by using images and set radar images and very quickly, very details. So Taipei Basin, our capital city, actually is threatened by many natural hazards, and right now most how to say scientists in Taiwan, we know that, but because this is well developed, so it's very difficult to displacement the capital city, to move the city to other places. So right now, the best way is that to study this area as detailed as possible and to predict the effect, or to predict the amplitude, to predict the best situation of this area, and then we can make our infrastructure, we can enhance all this infrastructure or make it more solid, and to prepare a good plan for one day the disaster occurred. Okay, so we cannot avoid this natural hazard, but we can study them and then prepare for them. Okay, I think that is my today's talk. Thank you for your listening. And if you have any question or you want to contact me, this is my personal contact information. Thank you to all of you. Thank you. Thank you.
Thank you, Professor Chang. I see there's 2 questions in chat room. Can you see that?
Let me check. Question table, could you talk about some common method? For the
Oh, Professor Chang, we can hear you.
okay, but
yes.
Okay, I see the question. The first question is that how to calibrate validate the raw result from PS SAR, GPS and leveling survey. It's a little complicated. I didn't talk too much about the detail because we cannot do the calibration directly. Actually, because the INSAR result is only, we can obtain only the information of a radar line of sight. So right now you have many methods to do that. For example, you can use this descending image and ascending image, and to compare these different radar line size to generate the vertical result, and compare that with other, for example, leveling survey. Leveling survey is a vertical one. But for the horizontal one, it's still very difficult. We need construct some model. So I think I cannot talk much the detail, explain the technique to you directly. Okay. And for the second one, let me check. Mohammed, question, which might contain different return signal generated. Yeah, that is a good question. Actually, before it's a little difficult because the information, I mean, the return signal is not enough for us to do the how to say classification of the land surface. But right now we can use different polar behavior. For example, we have a HV, VV, and VH radar, and to see the different return signal and to calculate to do the land surface calculation. Okay, that is possible. And right now there are some advanced satellites can see more details, and that will largely help us to do the classification. The answer is the answer is yes. And so I'm curious how is their accuracy is not so good compared with optical image, because the optical image can have so many different spectrum. Okay, so different spectrum you can obtain different information, and right now you have a hyperspectral image that can calculate so many can carry out so many information. But for the radar, it's not so advanced, so suitable. So we can do the clarification right now, especially for the, let me see, for the cope length. For example, for the right field, the radar is sometimes more useful than the optical one, because it can penetrate the rise and can see if there's still water under the rice field and so on. So, and it can determine the moisture. It's useful. It's more suitable than the optical image. But for most others, for the general classification, of course, the optical image, especially hyperspectral image, more efficient. Okay. Okay.
Okay, I see. Lin Chi-Hung, have you any questions? Lin Chi-Hung.
Okay, so good evening, Professor. So I have two questions for you. So the first one is, just like we know, this the satellites in the orbit. This is used the radar to scan the land. But my question is, the radar waves is not only output from satellite. In the land, that's the airbase, the airports, the airplane, they all have the many radar, and will be released the radar wave. This radar wave, they might be overlapping. So their frequency might be overlapping for this orbit satellite, and will lead to interference this satellite's image. So if will be this happens, how the satellite to solve this problem? So this is the first question. Thank you.
Okay, that's a good question. For the airborne radar, actually, of course, it's closer to the land surface, so normally the resolution can be higher than the satellite radar, and also the penetration capability, as I mentioned, is better than optical imaging, optical sensor. So it's very useful for the emergence event. For example, just after typhoon event, and the mountainous area or the land surface is covered by the cloud or smoke, and still you can acquire the good image and to do to help us to do something. But compared with satellite image, you know the orbit of the satellite is very, very precise. You can calculate the precise orbit, and based on this precise orbit result, you can remove the orbit effect and to do the INSAR and the DINSAR or PS INSAR technique. But for the airborne, you know, the track of aircraft is not so stable. Of course you can try to fix this aircraft along the right track, but still because of the wind, because of the GPS they result and so on, the airborne radar image is not suitable for the interferometric, I mean the DINSAR calculation. For the deformation, for this kind of measurement, it's very difficult. But we can fix the track very well and to calculate the tomography. That is possible. And the other way is that just like a SRTM, we scan at the same time. We put the two radar sensors, one on the wing and the other one in the center, and then scan at the same time. We can generate very quickly to generate a very beautiful topographic map. That is much rapid than if you know the LiDAR system, because LiDAR system scan one point by one point. That is we call it the cloud, the data cloud. So the calculation is quite waste of time. But by using the airborne radar, if you scan at the same time two radar sensors, you can generate the topographic map very, very fast. So each one have its advantage. For the deformation observation, still we have to use the satellite data. I say spaceborne radar. But for others, for example, to generate a local topographic map or for some urgent event, of course, you can use the airborne radar. Okay?
But even that happens, the radar release come from the airport or come from the airplane, their radar strength is still very strong. And the orbit satellites is very sensitive. In theory, they will be very sensitivity for this kind of radar interference. So how's this satellite to prevention their image don't do interference by this kind of strength?
Yeah, of course, the airborne radar signal is much stronger than the spaceborne. But for the spaceborne, we can still use for many things, and for the moment, for right now, we think that is enough. So it depends on what kind of study you want to do, just like that. So if you enhance the satellite to too strong, that is maybe will cause some problem, I think. Okay.
Okay. So my second question is so in the your slide inside the one image is the North Taiwan's the radar scan image. So this image inside, because this direction, so the sun is in the right. And I see that some strange is in this mountain inside the right part of the mountain, they will be brighter. And the left part of the mountain, they will be darker. So what will be this happen? Is it because the radar will release come from the sun? They have to illuminate the satellite image. Is that happen?
I know your question. Yeah. Sorry, I didn't explain that too clear. Actually, for the radar satellite, we call normally for the remote sensors, we call it as an active sensor. And for the optical remote sensing, for optical radar, optical satellite, normally we call it as a passive remote sensing. Okay, so the radar one is an active one, and the optical one is a passive one. The passive one use the satellite, use the sunlight to observe the land surface. So it doesn't. The optical satellite receive only the reflectance of the sunlight, and they use a different spectrum, calculate that, and so on. But the radar satellite, the satellite launch the radar wave by itself and receive the return signal of itself. So it's even in the night, there's no sunlight. The radar satellite can observe the lenses as the same method, the same result. So this result is another reflectance of the sunlight. It's directly from the radar signal. So the satellite pass through from the north to the south, pass through the eastern Taiwan, and launch the radar signal to the mountain. So the slope face to the east will return the signal directly to the satellite, but the slope toward the west cannot return the signal, or sometimes you will have some shadow. That is the radar it function. Okay.
Okay, thank you, Professor.
Thank you.
Thank you, Professor Zhang.
Thank you. So
Okay.
it's time to start today's lecture. Thank you for your listening.
呀，谢谢啊，那个
谢
郑老师，
谢谢大家。
Thank you so much.
李老师，拜拜。
Bye bye, Professor Zhang.
拜
Okay.
拜。
Okay. Everyone, please write down your answer word for these two questions in its Google form. The link we write down in chat room. You can check it.